Yeah, welcome. So in the last class, we have discussed about A-star algorithm, and also we have discussed about the what are the conditions for optimality for A-star algorithm. So we have discussed that the heuristic function must be admissible and also it should be consistent for A-star to be optimal. So an admissible heuristic is one which never overestimates the cost of reaching the goal state. And the consistent heuristic is given by this equation h of n, that is the heuristic cost from the state n should be less than or equal to c of n comma a comma n dash, which represents the cost of reaching from nth state to n dash state by performing an action a, plus the heuristic cost of reaching the goal state from the n dash state. So the sum of these things should be h of n should be less than or equal to the sum of these terms. Then we say that uh, the heuristic is consistent. Okay. To be more specific, the tree search version of there are again in A star also we have two versions. The A star algorithm can be of tree search version. It can be tree search version or graph search version. For the A star algorithm of tree search version to be complete, it should satisfy the property of admissible. If it is admissible, it is enough. The tree search version will be complete. I mean, it will be optimal, not complete. The optimality property for tree search is it should be admissible, and for graph search is it should be consistent. It should be consistent. Okay, a consistent heuristic is always admissible. Right? Fine. There is a proof for this, but so that is what is being explained here. But let us not get into that. Okay. So now we'll move on to there is a drawback with the Esther algorithm. The drawback, so Esther algorithm is actually it is complete and optimal. Esther algorithm is complete and also it is optimal. That is, it will find a solution and also it will find a best solution. But the drawback with Esther algorithm is the memory requirement. It may occupy more amount of memory, and the memory may not be sufficient. Whatever the memory available in the system, that may not be sufficient uh, to uh, to run the algorithm, um, to store that many nodes that is required as per the requirement of Esther algorithm. So the question is there any way to improve the algorithm so as to reduce the memory requirement? So we'll be discussing several variants of Esther algorithm. Basically, all these variants will be trying to reduce the memory occupied by the Esther algorithm. So this is one such variation of Esther algorithm, which is called as contours in state space. So this is basically an improvement that is done on Esther algorithm, and that improvement it works in the style of contour. So it is called as contours in state space. Okay. So let us discuss how this algorithm works. So this algorithm it puts an upper limit on the value of f. So f is nothing but our function. So so the evaluation function is for Esther algorithm is given as f of n equal to g of n plus h of n. So this function in short we are calling as f. So we'll put some value for f. So let us assume that we are the initial state is Aral, right? The goal state is Bucharest. So let us assume that we are keeping an f value of 380. It means that uh, we will consider only those nodes whose f is nothing but f of n, whose f of n value is equal to 380. Sorry, less than or equal to 380. We will consider only those nodes in the algorithm whose f of n value is less than or equal to 380, and will not include any nodes whose f of n value is greater than 380. Only if so So that is what we are calling as F value. If F is less than or equal to 380, those nodes will be included. Otherwise, it won't be included. Now you let us go here. So to calculate F, we need two things. What are the things we need? I mean, to calculate F, we need the so F is nothing but F of n, which is G of n plus H of n. So from Arad, we know that G of n is the actual cost from reaching the initial state to the goal state, which is 0. So H of n is the heuristic cost. So 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 the heuristic cost is 366. Okay, for from Arad, the heuristic cost is 366. Okay, so what is that? Uh, so it is 0 plus 366. So fine. So this is less than that. So this is I mean 0 plus. So for Arad it is 366, which is less than our F value. So Arad can be included, but nothing else can be included. If you see Zerind, actually we want that table. So let me go back here. Yeah. So I will copy this table so that we can easily refer it. Otherwise, every time accessing becomes difficult. Okay, so let it be here. Now we'll go back to the to this contour. So let us go through some other nodes. Let us take Z. Let us take Z. For Z, we will calculate the F value. So Zerin. Let us take Zerin. For Zerin, we'll calculate the F value. So F is nothing but F is equal to G plus H. So G is the cost of reaching the. So this is initial state. So that is 75. And what is H? H is the heuristic cost of reaching from Zerinth to Bucharest. So which is what? Which is 374. So 374 plus 75 is 374. What is that? 374 plus 75 is 449, right? 449. So this 449, if you observe, this is greater than 380. So Zerinth cannot be included. Now, can we include Timisora? So Timisora, if you calculate, its F value is its G value is initial state is Arad, so it is 118 plus what is Timisora? I mean the heuristic cost. So for Timisora, where it is 329. So again 329 plus 118, 329 plus 118. It is anyway it's greater than 380, right? 329 plus 118 is 447. So this is 447, which is again greater than 380. So we have certain F value for 380. So only if it is less than or equal to 380 we'll consider. Now if you see yes, which is nothing but CBU. So if you see CBU in the map, the cost of reaching. So if you calculate F for CBU, so it is 140 plus the cost of reaching from CBU to Bucharest. It is 253. So 253 plus 140. Again, it is 353, 393. 353 plus 40 is 393, right? So this is also greater than 380. So we cannot include any node. Only Arad is included. But now we have not reached the goal state. But we have reached the goal state. So with 380 we cannot achieve. So we have to slightly increase this. So we have to slightly increase this upper limit. So now we are increasing the upper limit. Instead of 380, we are going up to 400. So when you go up to 400, what will happen? What are the things we can include? Now also we cannot include Zerinth. We cannot include Timisora, but we can include CBU. So now CBU is added. When we make the thing to 400, CBU is added. Okay. but still we have not reached the goal state. So now we are making it to 420. So now we are making the upper limit for f as 420. See, now the moment you made as 420, when you make 420 also we cannot include Timisoara and Zarind, because as per this Timisoara is 447 and Zarind is 449. Okay, but there are other nodes which we have to check. So we have to check Rumin civil CA, Fagores, all these things. So what is the, for Rumin civil CA, if you calculate the F value, G is 140 plus 80, which is nothing but 140 plus 80 is 220. And H is, heuristic cost is from Rumin civil CA to Bucharest, it is 193. So 220 plus 193, what is that? 320, 420, 420 minus 7. So that is, I guess it is 413, which is less than 420. So this can be included. Similarly, if you see Fagores, 140 plus 99, that is 240, 239. So its G value is 239. And what is its H value? H value for Fagores is 176. So 239 plus 176, which is nothing but 239 plus 176. 239 plus 176 is 415, which is less than 415. So this can also be included, right? Similarly, we have to check. So Pitasti, if you see 140 plus 83, 220, 220 plus 97. 220 plus 97 is, what is that? 320, 320 minus 3 is 317. G value is 317. What is H value? Pitasti to Bucharest, it is 100. So it is 317 plus 100 is 417. Again, this is also less than 420. Okay, right? So like that. Now if you see Bucharest, there are two paths. Either you can take this way or this way. Let us take this way. So if you see this, it is 317 plus 101. 317 plus 101 is what? 417, 418. Okay, 418. That is a G. That is G, and H is 0 in this case. So it is 418 only. So Bucharest also included. This way Bucharest is included. If you consider this way, I think Bucharest will not be included. 415. So this is 239 plus 211. 239 plus 211 is what? 239 plus 211 is 450. So this way we cannot include Bucharest because our maximum limit is 420, right? And that is the reason here Bucharest is included. So the point is, now we are not, now we have reached the goal state and we have identified the solution. That too, we have identified an optimal solution, but we have explored very less nodes. We explored only 1, 2, 3, 4, 5, 6. We have not explored unnecessarily several other nodes. If you are using normal K-star algorithm, it might have explored Zarind, Horadia, Timisoara, all these things. All these we are not exploring. It might have explored Claveria. So lot of memory is reduced by this. So this method is called as contours in state space. So we put an upper limit on F. Initially, that will be a lesser number, and then we will gradually increase that until we reach the goal state. Okay. So this is one improvement on A-star algorithm. Right. So when we say that A-star algorithm is complete, optimal, and optimally efficient. So there are three things. So it's not only just complete and optimal, it is also optimally efficient. What is meant by optimally efficient? An algorithm is optimally efficient. A-star algorithm is optimally efficient because there is no other optimal algorithm which is guaranteed to expand fewer nodes than A-star algorithm. Okay. So because of this reason, it is optimally efficient. A-star algorithm is optimally efficient because there is no other optimal algorithm which guarantees to expand fewer nodes than A star. So you cannot identify another optimal algorithm which can expand less number of nodes than A star. Because of that reason, it is also called as optimally efficient. So the core drawback with A star is it may run out of uh, it may run out of space before it run out of time. Time complexity is also a problem, but the major problem is not time complexity, the space complexity. So that we have discussed here one improved version of A star, which is contours in space. Okay. So we'll be discussing some more improved versions of A star. So we'll be discussing memory bounded heuristic. So basically, these are subtopics of A star algorithm. These are the some of the techniques which are used to uh, reduce the memory requirement of A star algorithm. So how to reduce the memory requirements of A star algorithm? So there is one algorithm suggested which is called as iterative deepening A star. So this is like how we have ID A star. This is called as so iterative deepening A star is called as ID A star. This is similar to iterative deepening depth first search. In iterative deepening depth first search, initially we set the depth level as 0, then we make it 1, then we 2, so on and so forth. Similarly, here also this iterative deepening depth first search is nothing but it it's nothing but this contour search. So it is the contour search, but this contour how it expands in the sense, see in this algorithm we have what we have discussed, we have discussed that we are randomly increasing the contour. So this is contour. This concentric circles are called as contour. The size of the contour we are randomly increasing. We are not following any procedure. Like initially we kept as third 380, then we made 400, then we made 420. Is there any rule? No, it is something we are randomly adding. But what this particular IDA star algorithm says in the sense, what IDA star algorithm says means, say initially we kept 380. When you kept it, when you keep f is equal to 380, uh, only Arad is there. There is no other node is available because we are unable to include anything. Now, what the algorithm says in the sense, now the algorithm, what it says means the next value of f should be what is the node you can reach with minimum cost. So what is the which node we can reach with minimum cost, or not minimum cost, which is the node you can reach with minimum f value. So we have calculated here f value for everything. So the f value for Zerin is 449. F value for Temisora is 447. F value of what do you call F value of CBU is 393. So the algorithm what it says, initially we kept F as 380, but with 380 we are unable to reach anywhere. Only we have reached Arath, nothing else. So the algorithm says, the IDS algorithm says what is the next value with least F value you can reach. So that is we can reach CBU with a minimum increment of 39, making it 393. So now the algorithm says make f equal to 393. So now when you make f equal to 393, Arad and CBU will be included. Arad and CBU will be included. So from Arad go to CBU. You can go to CBU, but still we have not reached the what you call the goal state. So again from CBU you identify. Again from CBU, if you identify Fagaras can be reached with F value 413. I mean, from Fagaras, it is not reached. Fagaras is promising that it can take it to the goal state with a cost of 413. Sorry, Rumin Civil CO. Fagaras is promising that it can take with a cost of 415. Now, this also we should consider. Zerin 449, Timisora 447. So now which is the minimum? Now the one with the next minimum is, because now we are unable to the it is almost like the search has stopped, so we should increase the f value. So we will increase the f value to the next smallest available value. So what is the next smallest available? 413. So we will make f equal to 413. So it means this also included now in our thing, right? Now again you can continue. Similarly from Ramency, from we have to check what is for Cryovia, what is for Pitesti, all these things you have to check. So but we can also from here also there is a Pitesti path. So again which is the minimum, like that the algorithm will proceed. So that is what that is how this what you call IDA star algorithm is defined. It uses iterative deepening A star. Cutoff used is f of n equal to g of n plus h of n rather than the depth. So I mean in iterative deepening depth first search, it is depth. At each iteration, see read this. This is important. At each iteration, the cutoff value is the smallest t of cost of any node that exceeded the cutoff on the previous iteration. So at each iteration, the cutoff value will be the smallest f cost of any node that exceeded the cutoff of the previous iteration. So in the first iteration, our cutoff value is 380, but 380 only Arad is there. So now we have to increase the cutoff value. So how we are going to increase the cutoff value? So whichever is the next node, so cutoff value is the smallest f cost of any node that exceeded the cutoff in the previous iteration. So cutoff value is will be identified based on the smallest f cost of any node, right? So that is how we increase the cutoff. So from 380, why we go to 393? Because that is the smallest f cost we have. Other f costs are greater than that. So whichever the available smallest f cost, that will be made as the next cutoff value, right? But this algorithm works well with unit cost or unit step cost, but it suffers with serious drawbacks when with real valued cost. As long as the cost is unit cost, it works fine. But if it is real world, no, if it is real valued numbers, it may not be best, right? So that's the drawback. If it of course reduces the memory requirement, but this is one of the drawback with this technique with IDA star. So next we have another algorithm which is called as recursive best first search, RBFS. So already we have discussed what you call. This is not breadth first search. This is best first search. It is recursive best first search. So this algorithm is similar to recursive DFS. It uses something called as F limit. It uses something called as F limit, which helps to guide the algorithm. So let us discuss the algorithm. I mean, not let us discuss with an example, then things will be clear. See, for every node, we will calculate a F limit. Not for every node, the node which we are going to expand. The node which we are going to expand, we will calculate the F limit. For the initial state, the F limit will be infinity because we don't know initially what is F limit. So I mean, here there is no other equivalent nodes. So because of that, for the initial state, the F limit will be infinite. So we are starting with Arad, which is the initial state. So its F limit is infinite. Now for Arad, we calculate F of n. F of n equal to g of n plus h of n. What is that? That is, we have calculated several times, that is 366. Right? Now from Arad, what are the possibilities? We can go to CPU, Timisoara and Zerinth. And these are the F score. This is the F score for CPU. That is g of n plus h of n. This is 393. And this is the F score for Timisoara, which is 447. This is the F score for Zerinth, which is 449. Now from all these things, we'll pick up the minimum cost path. Minimum path is what? CPU. So how we got this 393? So that you know, right? So that is the cost of reaching from Arad to CPU plus the heuristic cost of reaching from CPU to Bucharest. So yeah, so this is 140 plus 253. Right? 140 is the cost of reaching from Arad to CPU, and 253 is the heuristic cost. Like that, For everything it is calculated. Timisoara and Zirind also, it is available here. The Timisoara is 447, Zirind is 449, right? Okay. Now this path we are going to explore. But before exploring what we are going to do, here now we are going to add the F limit. For the initial node alone, there won't be F limit. For other nodes which we are going to expand, we will be adding F limit. But what is this F limit? How we got this F limit? This F limit is the next best path in this same level. So this is the best path in this level, right? But what is the next best path? Suppose if 393 is not the best path, then what is the next best path? It is Timisoara. What is its F score? 447. And that will be the F limit. That will be the F limit for the path that we are going to explore. Is that clear? So this 447 comes as the F limit of CBU. Okay. Now we expand CBU. When you expand CBU, these are the possibilities. Arad, Fagaras, Oradia, Raminsu will see. Now for everything, we are calculating the F score. We already did this several times, so I don't want to repeat it. So this is how we got this. It is again g of n plus h of n. G of n is Arad to CBU, CBU to Arad plus the h of n of Arad to heuristic cost of reaching from Arad to Bucharest. Similarly, we are calculating f of n for Fagaras, f of n for Oradia, f of n for Ruminsivilsi. Now, out of all these things, out of all the unexplored paths, I mean, out of now we are not this algorithm. Yes, so this algorithm is not yeah, out of all the unexplored path, which is the smallest cost, which is the which path says that it will take to the destination with the least cost. So this path says Rumins will see. So we are going to, because Rumins will see cost is 413. So this is its F cost. So we are going to expand this. But before expanding, we should add the F limit. What is the F limit? F limit is the next best cost in the same level. F limit is the next best cost in the same level. So what is the next best cost in the same level? Fagaras, that is 415. That is its, what you call, that is its F limit. Now we expand Ruminsivilsi. So when we expand Ruminsivilsi, we got all these things. Craiovia, Pitasti, CBU. For all these things, we calculate the F score. So F score for Craiovia 526, Pitasti 417, CBU 553. Now out of this, out of all these things, which is the smallest one, Pitasti 417. But here you have to check one thing. See, whenever, see, this is 417, but previously Ruminsi will see what it is. Previously in Ruminsi will see what is the F limit? 415. Here we are. This is the reason why we are storing the F limit. Please understand why we are storing F limit means. So there is, at Ruminsi will see at this level, there is some other node which is promising that I can take you to the goal at the cost of 415. But here already our cost has become. But Pitasti is now promising that it can take to the goal at the cost of 417. But this 417 is greater than 415. Is that clear? This 417 is greater than 415. So now the algorithm will go here. It won't expand this. It won't expand this. It will go to Fagaras, right? It won't expand this because there is another better path available, right? So it will go there. So the algorithm will shrink this tree. This part it will shrink. And one more thing it will do. Now this F limit will be changed to 417 because we have already explored up to this, and Pitasti is promising that it can take at the cost of 470, not 415. So this F limit will be changed to 417, and this path will be shrinked, and the algorithm will go to Fagaras, right? And it will start exploring Fagaras. So that is what is happening here. So previously, whatever 415, the I mean the so sorry, it is not it is not changing the F limit, it is changing this cost. So Rumins will see previously it promises that it will take to the goal at the cost of 413. Okay. So now this will be changed to this 413 will be changed to 417. But here comparison is made with this. Why we are making with this? Because this is the next best path. So if this is not the best path, then there is another best path available. What is that? Through Pythagoras. Pythagoras is promising. That also we don't know. Because all f value is a combination of two things, g and h. G is the true value and h is the heuristic value. So, but anyway, this promise is better than this promise, so that we are going back. But before going back, we are making some changes. What we are making? Previously, Ruminsu will see as f score is 413, which we are making up to, which we are making to 417. Because with Pitesti, we know that at least it will take 417. No, it not at least, but it may take 417. So it is so it is because already we have come down one level, and it is saying that it will take 417. So we are changing this to 417. So that is what here it is happening. So this 413 previously whatever 413, it has now become 417. Now we are going to explore Pythagoras. But before exploring Pythagoras, we have to specify the f limit. Now f limit is always the next best path in the same level. So what is the next best path? This remains we will see as the next best path. So this 417 we are moving it here. And now we are expanding Pythagoras. When you expand Pythagoras, you got CBU at the cost of 591, Bucharest at the cost of 450. Out of this, which one minimum? Bucharest is minimum. But still, Bucharest is the gold state, but we are not checking now gold test. We are going to check the gold test only during expansion. So again, which is the minimum cost 450. This again, we will check whether this is greater than this F limit or not. Yes, it is greater than F limit. Whenever you identify a path, the least cost path which is greater than F limit, then we will shrink that. So again, this entire thing should be shrinked. Now this 415. So Pythagoras is promising that it can take to gold state at the cost of 415, but it is not possible because here you are reaching Bucharest at the cost of 450. So this 415 now will be changed to 450. 450. And what is the next best path available? Via Rumins will see. So once again, this will be explored. So algorithm is going back to from Rumins will see it goes to Pythagoras. Again, it is coming back. So again, Rumins will see will be explored. Right now, now this is 450. Okay. Now what is the what is the f limit of Rumins will see? So f limit of Rumins will see is now what is the f limit of Rumins will see? Yeah, it is the whatever the least cost. Okay. So is there any so so Rumins will see is promising that it can take it to the gold state at the cost of 470. So f limit will be something the next best option. So what is the next best option we have? The so it's not only this level, the whole tree we have to check the next best level. So what is the next best level we have? So the next best level is for CBU. CBU is so this is 671, 450, 646. CBU is promising that it can take at the cost of 447. Okay. So the next best cost what we have is 447. So this 447 comes as F limit. Okay. So now we expand this. So we got Craiovia, Pitesti, and CBU. So this is the F value. So what is the F value for Pitesti? 417. Is 417, is it lesser than the F limit? This F limit is not yet added. Is it less than the F limit? Yes, it is lesser than the F limit. Okay. So now we are going to expand Pitesti. So before expanding Pitesti, we should add F limit for Pitesti. So what is the F limit for Pitesti? So what is the next best cost available. So the next best cost is this only 447. So that is coming here as the F limit. So now when you explore Pitosti, you got all these things. So Bucharest at the cost of 418, Craiova and Prumince will see. Now Bucharest, what is the cost? 418. So is this is lesser than the F limit? Yes, it is lesser than F limit. As it is less than F limit, now we can expand. But before expanding, it checks whether it's a gold state or not. Yes, it's a gold state, so the algorithm stops. So if you see, actually this algorithm is, so in A star, in A star also, first the algorithm went through Fagorus and then it will turn back. Okay, but there it will go fully. Fagorus will be fully explored up to Bucharest. But here we are not doing that, right? And whenever a path is a path is exceeding beyond the F limit, we totally shrink that. We remove all these nodes. So it means all these nodes are removed from the memory. So that is how it reduces the memory. Okay. So this is how RBFS works. That is recursive best first search works. So basically this is an improved version of A-star algorithm to reduce the memory. Okay. But there is there is a interesting drawback with ID A-star and RBFS. You know what is that? Actually, ID A-star and RBFS, it uses too little memory. Too little memory. So this also you cannot call as efficient usage. See, efficient usage means what? You have to use mostly, then only it is called as efficient usage. Otherwise, it is not efficient usage. So it is something you have the resource, but still you are not using it. So when you have the resource and if you don't use it, it is as if you don't have the resource. So now the problem with IDSR and RBFS is it uses very less amount of memory. It is as if we have a lot of memory, but it uses only very less. So we are wasting this memory. Okay. So this is another drawback with IDSR and RBFS. The drawback with A-star is it will run out of memory. But IDSR and RBFS, it uses too little memory. So there is another version of A-star is suggested, which is called as SMA star, simplified memory bounded A-star algorithm. What this does in the sense, it simply executes A-star algorithm. No refinement, nothing. It simply executes the A-star algorithm until the memory becomes full. Until the memory becomes full, it executes the A-star algorithm. When the memory becomes full, it drops the worst node. It deletes the worst node. The moment memory becomes full, it deletes the worst leaf node. Okay. So what is the worst leaf node? The worst leaf node is the one with highest F score. If F score is high, then that is the worst node, because it is saying that it will take to the goal at a high cost. So that is the worst node. So such a node will be deleted. Suppose if more than one node is having the uh, if 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 more than one node is having the highest F value, that is if more than one node is the worst node, in that case the newest leaf node will be expanded and the oldest leaf will be deleted. Okay. So if there are three leaf nodes and all the three are left, all the three are say node 1, node 2, all these three leaf nodes are worst nodes. That is their F value is high and they are also equal. Say their F value is, all these three nodes, the F value is 120, 120 and 120. Now all these are leaf node. They are the worst nodes. Now which one will you keep and which one will you drop? So the newly created child will be kept and the oldest leaf will be deleted. First the oldest leaf and then we continue the algorithm. Again, if it is full, then again drop the worst node. So that is how the algorithm proceeds. And it does one more thing. See, before deleting, before deleting, it will pass on its value. It will pass on its forgotten value to its parent. Like RBFS, SMA star then backs up the value of the forgotten node to its parent. In this way, the ancestor of a forgotten subtree knows the quality of the best path in that subtree. Okay. So why it is sending? Because at least this parent knows like what is the cost of reaching here. right? So so its forgotten value means its f value. So before the node gets deleted, its f value will be passed on to its parent, so that the parent node knows, if I follow this path, what is the expected cost, right? So this is how the SMA star works. So that's it about today's discussion. But before closing, I would like to share few things. There, this is something which I want to discuss. Okay. So for the problems with, so this is we will be discussing slightly about the time complexity of Escher algorithm. Actually, Escher algorithm suffers with both time complexity and space complexity. It is complete, and also it is optimal, and also it is optimally efficient, right? All these three things are there, but still it suffers with time complexity and space complexity. Again, space complexity is a bigger problem than time complexity. But this slide here will be discussing something about the time complexity. In Escher algorithm, for problems with constant step costs, the growth in the growth in the runtime is nothing but the time complexity. The growth in the runtime as a function of the optimal solution. Let us assume the optimal solution is available at depth d. So this time complexity is basically analyzed in terms of absolute error and relative error of the heuristic. So the time complexity of Escher algorithm is analyzed based on two factors. One is absolute error and the other one is relative error of the heuristic. Absolute error is given like this: del is equal to h star minus h, where h is the where h star is the actual cost from the root node to the goal node. Okay, and h is the heuristic cost. H is the heuristic cost from the root node to the goal node, and h star is the actual cost from the root node to the goal node. So h star minus h, that is called as absolute error. Relative error is h star minus h divided by h star, that is relative error. Again, these things are same, that is, it is the actual cost of reaching from initial state to the goal state, and h is the heuristic cost, and this h star is the uh, again this is the same. Okay, so relative error is given as h star minus h by h star, and the time complexity of Escher algorithm is order of b to the power epsilon d, where d is the depth at which the solution is available. But this time complexity is based on absolute error. Okay. So there are actually two different time complexities. So we are not discussing the time complexity with respect to relative error. The time complexity with respect to absolute error is order of b to the power epsilon d, where d is the depth at which the solution is available, and epsilon is some constant. Okay. So then coming to SMA star algorithm, that is simplified memory bounded Escher algorithm. So this SMA star is complete if there is a reachable solution. So what is SMA star? SMA star will simply run A star algorithm until the memory becomes full. Once the memory becomes full, it will it will remove the leaf node. It will remove the worst leaf node. If there are more than one worst leaf node, then the newly generated leaf node will be kept and the oldest node will be removed. So that is how basically it works. And before deleting the node, its forgotten value will be passed on to the parent. Right. So this is complete if there is a reachable solution. Reachable solution means what? Because sometimes you may go out of memory. So if the solution is reachable, then it is complete. That is, if d, the depth of the shallowest goal node, is less than the memory size, right? So d is the depth of the shallowest goal node. So the depth at which the shallowest goal node is available, if it is less than the memory size, then it is optimal. Then it is complete. That is, it will find a solution. It is optimal if any optimal solution is reachable. Again, it depends on the memory. That is what it says. It is complete if there is a reachable solution that is at depth d, where d is the depth of the shallowest goal node. It is optimal if any optimal solution is reachable, right? That is within the memory limit. Otherwise it will return the best reachable solution. So it means that sometimes the best solution may be at a deeper level. So it is not that the best solution always should be at the top level. So it all depends on the cost. Okay. There is one drawback with SMA star algorithm. The SMA star algorithm is forced to switch back and forth continually among many solution paths. Only a small subset of which can fit in the memory. So see, we are allowing the algorithm to expand until it occupies full memory. Then we are dropping the leaf node. So once you drop the leaf node, now the algorithm may take different path. So like that, whenever the memory is full, it will drop some node and it may take different path. So this process is called as this is called as thrashing. This is similar to thrashing. So it follows a path, but when the memory is full, then it removes that and it follows some other path. So this is similar to an operating system issue, which is called as thrashing. We'll be discussing about thrashing in operating system. So basically, thrashing means when the when the assume memory is full. When memory is full, the operating system will try to swap. But but at some situation, what happens? Say the memory is full, the operating system will try to swap. That is, it will identify some block of memory. It will take that to the hard disk, and it will bring some new part to the main memory. But once again, there will be some requirement from some process. Again, the memory is full. Once again, you do swapping. So once again, it will do swapping. So if the operating system is continuously doing swapping, that is called as thrashing, because then the operating system or the CPU is spending more time in swapping rather than in computation. If a CPU or the operating system spends more time in swapping rather than in the actual computing task, that problem is called as thrashing in operating system. Similarly, the SMS or algorithm also, it may keep on do this. The memory is getting full, follow some other path. Once again, memory gets full, follow some other path. So like that, it may keep on do this. So that problem is called as thrashing. With thrashing, what happens in the sense, uh, the problem may become intractable. Actually, the only problem with the algorithm is it is the memory requirement is the major problem. Otherwise, it is optimal and it is complete, that we know. So assuming you have unlimited memory. Say let us assume we are using A-star algorithm and we have unlimited memory. Then actually A-star algorithm is tractable. That is, it will find a solution, right? So the problem that would be practically solvable by A-star algorithm given unlimited memory. If unlimited memory is given, then any problem is solvable by A-star. But the same problem may become unsolvable. That is, intractable means unsolvable for SMA star, because SMA star sometimes it may get into this thrashing problem, right? So basically, it means that memory limitations can make a problem intractable from the point of view of computational time. Okay. So because of memory limitation only, this problem is happening. Because of memory limitation only, we are going for SMA star. But when you, but when the memory is full, if you remove the node, then the algorithm's working style will change. But again, the memory may become full. Again, its working style may change. So like that, if it continuously happen, then the problem may become insolvable or intractable, right? So, but originally, as per ESR algorithm, the problem is tractable, provided an unlimited memory. But with SMA star, the problem may become intractable. Fine. So that's it about today's session. We'll stop here. Thank you.